Okay, welcome back. And today we'll be going over 11.9. Okay, so let's talk about 11.8 first. We defined what we mean by power series. Try to recall, we have a function. We want to rewrite it to be the sum of a lot of powers. And then we first defined what we mean by power series, which is basically a polynomial. A more general case look like this, with a coefficient and the power part, which is a power of x. And we can shift it left and right by a center. Okay, for example, if you have something like x to the n, it goes to x minus 2 to the n. It's basically the same thing, but you shift to the right by 2. Okay, so that is called a center. Then we talk about the interval of convergence, which basically means if you want to write a function into a power series, sometimes it works, sometimes it doesn't work. It only works when the thing on here, which is a series, is convergent. So to determine that, we do the ratio test. We set it to be less than 1, okay, after we finish all the computation, and we will always end up with inequality. Okay, I'll just skip the details. Less than 1 to find where it's convergent. Therefore, our answer will always be an interval. It's either going to be a single point, or it's going to be negative infinity or infinity, or it's going to be starting from A, go left by R, and go right by R, which is the interval centered at A. Then we say this R is called the radius of convergence. That's what we know about power series. Okay, we know the definition. We know how to check when this one will converge, when this one will diverge. And then there's one thing lacking. That is, if I give you a random function, how to find the power series representation of it. Okay, how to find the actual coefficients to define the power series. Once we define it, taking the derivative, taking an integral, doing everything will become easier. Moreover, we can take finite terms and use a computer to approximate any function. So that is the beauty of it. So for 11.9, we will focus on this part. Giving you a function, how do you find the power series representations? And we start with a very special example. So we are going to write everything in this section based on a base formula, which is the one I just wrote down. Okay. The reason we have this, again, to recall a little bit, is because we have something like this. Very easy. Then we realize this is a geometric series. R equals x. Therefore, to use the formula a1 divided by 1 minus r, which is 1 for a1, 1 minus r, which is x, that's how we get this power series representation. Moreover, we know this one converges if the absolute value of x is less than 1. Okay? So with everything we have from this section, we will be focusing on anything related to this formula here. It will be very restrictive, but we can already do a lot of things which are interesting. Okay? Now let's try some examples. The first one is going to be this. Let's think about it. You do know how to do this. That's the formula we know. Okay. Now what about this? Take a look at them. Do you realize they are actually pretty similar? So what you can do is you can use the form we just wrote down, but plug in this to be your x. Then it's nothing but sum. Look at the difference. If you put x here, you got this formula. If you put negative x squared here, you simply just plug this one into this formula to get. That will be the answer. Okay, so a simple substitution. If you really want to see what it looks like, it's actually if you plug in 0, it's 1, and plug in 1. That will be the power series representation of this thing we just wrote down here. Okay, kind of makes sense here. So basically what you do is you try to find, you try to find a formula which is similar to this, and then you just substitute what you need to do. Okay, that gives us some restrictions. That means the thing we're trying to do must look somehow similar to what we already know. Let's try another example. That one is already good. Okay, now let's change things a little bit. If I do this, now you know you just take this part, make it minus x squared, put this one into x, the formula is done. Okay, now let's take this one, but let's change the top to be 3. Okay, still coming from here. That's the formula we know. Okay. Now we want to somehow make this one look like this. Oh, the other way around. Then of course we know we should make the bottom 1 minus this to plug in here to make it happen, if it's this case. Now we change the whole thing here to be 3. And here we have 1. So what do you think? How can we do something in addition to make this 1 to be 3? We simply just times it by 3. Then we times everything on the right-hand side by 3. This is actually also very easy. From here you can see changing the number on the top. Really, you just need to multiply the whole thing by a certain number. So that is not hard. Okay, now let's do something even more tricky. Which keep this one to be 3, and it's already good. But now I want to change this one to be 2. Okay, we still do the same trick. Now we know the 3 on the top, we just multiply by 3 later. It's not difficult. But what about this one on the bottom? Well, if you think about it, this 1 here is essential because it comes from a1, 1 minus r, right? This 1 has to be a 1. So there's no way we can change this 1. That means if you have a 2, this one has to be 1. So how do you do it? Well, how about we just make it 1? And we factor out a 2. But that will also change this part, which I'm sure we will be fine. So this is the first thing we did. Then we factor out 3 over half times 1 over. Now we have 1 plus this. We can change it to be 1 minus. And I think up to here, it's 1 over 1 minus x format, except your x is replaced by this. Okay. Now, if you think about it, this is nothing but 1 minus x over 2, if you plug in 1, and then plus x fourth over 2 squared minus x to the 6 over 2 cubed, and dot, dot, dot. Clearly, this is a nice power series, and this will be the power series of the thing we just wrote down here. Okay, so note, the difference will be this is going to be a 3. That's no big deal, just times 3 when you finish. Okay, this is going to be a 2. We want to change it to be 1, and the best way to do it is actually factor out a 2. Then this one become 1, but when you factor things out, this part change also. But actually, if you change this part, whatever you change to this part, as long as you can eventually write it down to be 1 over 1 minus x, which is 1 over 1 minus x format, here, you will always be able to do it. So that's roughly the idea of how to do this. Just change all the coefficients to make sure they match. Okay. Now finally, let's try a harder problem. That is x to the cube over 2, let's change it to be a 3, plus x squared. Now let's make it x to the 4th. From here you can see it really doesn't make things any more complicated. Now let's think about it. Okay, what is this? Well, technically, we want the formula. Okay, this one doesn't look like it. Let's change something. You want it to be 1, so you probably want a 3. Okay. You want it to be minus, then you probably want to change this to be minus. Okay. On the top, you want it to be 1, but this one is x cubed. Before, if this is a number, you just times a 3 times a 4. This time, it seems like you don't have any other choices, so probably you want to times x cubed. It looks weird, but let's just go ahead and try to do it. If the answer ends up being good, we don't have to do anything. So 1/3 x cubed 1 over 1 minus this. Now if you focus on this part, can you see it's 1 over 1 minus x, except this one is changed to whatever I wrote down there. So I can go ahead and give this. Okay, now this is basically over. But now what you can do is you still have a power here. You want to somehow merge this one into everything inside. There are several things I want to mention. The first one is, let's simplify things a little bit more. Okay, this is going to be negative 1/3, which will make the whole thing alternating, and x to the 4n. Okay, this is my simple power law. Now after we do that, let's see what this really is. It equals this one times this, where you have, if you plug in 0, it's 1. Okay, actually, if you plug in 1, it's x to the 4. If you plug in 2, it's going to be plus, minus. So basically, if you just look at this part, you have x to the 4n. That means you start from x to the 0, then x to the 4, x to the 8. You add 4 power of x every time. Your coefficient is going to be alternating. It's going to be a power of 1/3. Everything's good so far. Now you want to times this whole thing by x to the cube. What do? You simply take this one and distribute it to every single term. So you have 1/3 times x cubed minus x7 plus 8 plus 3, x to the 11 minus x to the 12 to the cube. So x to the 15. And keep going. Do you realize when you distribute this x to every single term, the result is every single term, the power raised by another 3. Make sense so far? So what you need to do is simply take this one, put it inside, because this one goes with every single term as your n change. So every single term is going to be added another 3 inside. Okay. That's how we actually simplify this thing further. That's why I want to take this negative 1/3 out, because your x to the cube should go with x to the 4n, not this one. Okay. Otherwise, no, sorry. If you just go with this, it's really hard for you to merge because you still have negative and 1/3 here. So that's why I actually take 1/3 out. Then you only have x to the 4n. It's easier to merge this one with x3, which is x to the 4n plus 3. Okay? So the computation seems trivial when you have x to the cube. You just add every single term with a cube. But for some of you, it may look confusing at first. Okay? So I would strongly suggest write down every several terms, like 4 or 5 terms here. Try to see what this x to the cube do. Once you realize it add a cube not just for one term, but for every single term, then you can put it inside, because this one, as long as you plus a 3 here, that means every single term for every n raised by another additional 3. Okay, so that is probably the most complicated examples we can have. That is, we go from here, number 1, this one can be plus. Number 2, this thing can change. Number 3, this one can be a different number. Number 4, you may have something on the top. Okay, the thing on the top, you just multiply them. The thing on the here, try to make it 1 by factoring things out. Whatever you have from here, then you just take it minus. Whatever you have here, just make it. Okay, and then plug this part into the original formula. You will always be able to solve things like this. But again, it's a very big restriction. That is, you can only solve things which look like this. Okay. But it's already a lot, as far as you can see. Of course, every single one I wrote down here, though they have an interval of convergence. The thing I write down here, interval of convergence. The thing I write down here, interval of convergence. To save some time, you go ahead and try to do it yourself. Okay? I think you should practice at least for all these examples, because in the exam, I will definitely ask you to find the power series. And then I will ask you either find the interval of convergence or the radius of convergence. So try to do that. Okay? So far, so good. Should I? Later, I will give you the answer of each one. Okay, even though I won't show you the steps, I will give you the answer in the notes later, so you can actually check your work. Okay, so that's some examples. Basically, we try to go with this. Try to match whatever to be as close you have to be as close as the formula we have. Now let's see number 4, which becomes super interesting. That is, what is this? Okay. Let me actually write it to be here. What is this? Okay, in terms of power series. Now, if you think about it, we try to associate this one with the formula we know, which is 1 over 1 minus x. The question becomes, do you know any functions which is related to arctangent, which also look like something similar to this? Pause a little bit, think about it, and do you realize it's actually this one? It will be very similar to this. Now, if you think about it, this one is basically 1 over 1 minus x squared. I can certainly find the power series of this one. Okay. But what's the relationship between these two? This one here is going to be the derivative of arctangent. Once I know the power series of this one here to find the power series of this one, then all we need to do is just take the antiderivative from here. Then we will be able to find this one. Okay, so let's actually do the logic here. Arctangent, you want the power series. What you do is you take the derivative first. You have this. Then for this, you find, oh, I can actually find the power series of this one. Then to find the original power series, you just need to take the antiderivative. Let's see the logic. Arctangent, go to arctangent's derivative, find the power series of the derivative of arctangent, take the antiderivative to find the power series of the original arctangent. Okay? Similar thing works for the other one. For the other way, I will just give you the example here. Take something like this, for example. This is not something we can do. But take a while, you will realize this is going to be the derivative of negative 1 over 1 minus x. Actually, there's no negative. Okay, and this you can do the power series. So if you are thinking about doing this one, we can first take the integral to get this one. Do the power series of this one. But when we finish, we take the derivative back to find the power series of this one. Sounds good? Okay, so that's actually some examples we want to do next. That is, this examples, all the examples we did so far, looks similar to this. But even for something which doesn't look similar to what we have here, but it will look similar to what we have here. If we take the derivative and antiderivative, it's still doable. Okay, so let me show you how to write this down. Number one, take the derivative of this. We do have this. Okay, number two, this one can be written as a power series. Okay, now if the power series of this one is this one is the derivative of arctangent. How to find the power series of the arctangent? Now you just need to take the integral. Okay, of this one. But this one has a power series. Okay, so we just need to take the antiderivative of this, and then we're all set. Good so far? Okay. Now, if you take the integral of a power series, is this still a power series? Let's take a look. Let's see how do we take the integral of this thing. This thing is basically 1 minus x squared plus x squared plus x to the 4th plus x to the 6th, dot, 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 right? To take the integral of this one together is nothing but to take the integral of 1 and x squared and x to the 4th and x to the 6th. If we want to write one more, it's going to be this, dot, 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 dot. It's actually nothing to take the antiderivative of every single one of them. Okay, that means you can take the sum and then take the integral, or you can take the integral of each single one and then sum them together. So what we can do is we can interchange the sum sign. Okay, be careful with what I say. You can do the sum first, then you do the integral. And then we claim it's the same as do the integral of each one, and then take the sum. Okay. It's true, it's trivial. Then we can interchange these two signs. We do the integral first. Then keep the sum sign. You're just asking yourself how to do the antiderivative of x to the 2n. It's going to be x to the 2n plus 1. Just like the way we take any for any power series. Okay, which is the same for any n you plug in. Okay, so by doing this, you just took the antiderivative of every single term of the original one. If you don't believe it, write down the sum, try to see it, and see if it makes sense. Okay, write down the first 5 terms. Try to see if it makes sense. This should be the answer. Does everything make sense so far? Good. If that's the case, some side topic. When you take the integral, if you don't have ending points, do you realize you do have a plus c? Okay, so what does it mean? That means this one will be the derivative of arctangent. It will also possibly to be the derivative of arctangent x plus 3. And just taking the antiderivative, you really don't know which one is which. So we make a small mistake here. There's no guarantee this one is going to be arctangent x. This one is going to be arctangent x plus a constant. And we're good so far? Okay. But we want the particular one which equals arctangent x plus 0. Then what we should do is we should really go ahead and solve for c. We want arctangent x, and we know arctangent x should equal to this one, plus some constant. We just don't know what this constant is for this one particularly. Okay. Then we can simply just plug in some x and try to solve for it. For this case, I propose plugging x equal to 0. Then arctangent x equal, actually 0, equals, if you plug in 0 here, the whole power series will be gone. So then C should equals arctangent 0, which is 0 in this case. So finally, plus a 0, which means we don't have to write it down. This will be the power series of arctangent. Okay, so let's go back and try to see several key points. The first one is you see arctangent, you take the derivative to get something similar to the formula we want. Then we go ahead and try to find the power series of this one, which is standard. Okay, the answer is here. Once we got this answer, how to get the power series of arctangent from it? Well, since this one is the derivative of arctangent is the integral of this one. Okay, then we just simply take the integral. The good news is, if you have a power series, you take an integral, it returns to a different power series. This which will very likely to be the power series of arctangent. Now the only thing you are not sure, just as anything you're trying to do with the integral, you need to plug in a number to figure out what C is. So this is essential. You cannot simply ignore it, okay, or skip it. This requires some calculation. For this case, you have C equals 0, but for some other cases, you may have C equals to some weird number. Okay, so just make sure you do this step whenever you do the integral. Okay, go back, work on this, and think about it. Okay, now let's think about another different example. I just want to make sure it's complete. This thing here. Number one, we do want something like that. If you put a square here, it's still fine. But if you put a square on the whole thing, it fundamentally changes the structure. So at first, this one should be seemingly impossible. But then we realize we can take the antiderivative, or we can take the derivative, do the power series, and transfer back. It will take you a while, but eventually you realize this one is nothing but the derivative of this one. Okay. That means if we find the power series of this one, and then we take the derivative, we will have the power series of this one. For that case, we actually have a really nice one for this case. Now we just need to take the derivative of this, which is nothing but the derivative of this. Again, what we want to do is we want to take this and take the derivative of the inside instead. That means we want to interchange the derivative sign and the sum sign. Can we do that? Well, let's write it out. It's 1 plus x squared plus x cubed plus x to the fourth dot 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 dot. Then you take the derivative. You take the sum first, you take the derivative of the total sum. Now with our experiences, we know we can actually take the derivative of each one separately. When we finish, we just sum them together, which is fine. That means we can take the derivative first, then take the sum. We can interchange these signs. But once you have that, since you're going to take the derivative of every single one, why don't you just take it for this general formula, which is nothing but n times x to the n minus 1. Okay. Then we claim the power series of this one is going to be the power series of this one. How did you find it? You find the power series of this one first. Then you take the derivative of this one, you get this. Then you take the derivative of the power series, you get this. And they should be the same. That's how we find the power series, by taking a d-tool. Sounds good? Okay. We will do one more example after this, but let me summarize what we just did. That's actually the second part of this thing. The first part is, if you have this formula, you just look for something which looks similar to the formula. Transform it a little bit until you have exactly 1, 1, and then minus something here. Okay? That's algebra. Now what if you have something which is not so close, which actually involves taking the derivative or taking the antiderivative? Okay, so basically what you want to know is how to take the derivative or antiderivative of a power series. And this is what it tells you. Okay. Several interesting things. Number one, the formula looks like this. Then the derivative equals this. From here you can see Cn is a constant, so it doesn't change. Okay, what you did is basically take this part, take the derivative, that means put the n power down to be an n, and reduce the power by 1, which gives you n minus 1. Similarly, when you take the antiderivative, you actually raise this power by n plus 1, but then you put a number here to cancel what you have there. So that's exactly how we take the derivatives and antiderivatives of a power series. Fairly easy. The Cn stay the same. Okay. Now, the only difference between derivative and antiderivative is when you take the derivative, you don't have a plus c. When you take the antiderivative, however, you do have a plus c. So if you try to find the power series through taking the antiderivative, you need to do some additional steps. That is, try to figure out the c. So let me put it here as a note. Find c afterwards. Okay. The third thing becomes super interesting. Now think about what we have before. Okay. Let's think about our arctangent one. Okay, let's redo this logic. Arctangent x. You take the derivative, you have this. You have a power series. What did I do? I made a mistake here. I need to correct it. Okay, this should be negative x. Negative x to the square n, which gives you negative 1 to the n, x to the 2n. So I'm missing a negative 1 to the n here. Which should be okay. Okay, so I do have this one. Let me correct it. I have negative 1 to the n, x to the 2n. Now I take the integral. I got some cool. Okay. So now here's the interesting part. We have two series. The first series will be the arctangent one. The second series will be the one for the derivative of arctangent. Now you know the series will only work if the whole thing is convergent. So this one is going to have an interval of convergence. This one here is going to have another interval of convergence. Now the question becomes, will these two intervals of convergence to be the same? will this one to be smaller than the original one or bigger than the original one? That is a very serious problem, because if these two are not the same, they can be very different. Let's say if you take the antiderivative, the whole thing shrink. That means there are some number you can plug in here, but you cannot plug in here in order to actually calculate it using power series. Our instinct should be, if you can plug in something number here to approximate this, you can probably plug in the same number here to approximate this one. Otherwise, you have to be super, super, super careful. Okay? And the good news is, by the theorem, the third part, they tell you the radius of convergence before and after you take the derivative stays the same. That means these two will basically share the same interval of convergence. So if you can plug in a number here, let's say you can do 3.3 here, then 3.3 here will probably be safe. Okay? So the interval of convergence is almost the same as the interval of convergence before and after you take the derivative. Okay? The only difference will be the ending points. Because the theorem says R will stay the same. That means before you take it, it may be A minus R, A plus R. After you take it, it will still be A minus R, A plus R. But maybe some of the parentheses will change to bracket, and some of the bracket may change to parentheses. But that will be the only difference. Okay, so that's what the theorem says. To see why this is true, it's actually not hard. Let's take these two examples. Let me copy the theorem here. We know if we have this, okay, if you take the derivative, it becomes this. If you take the antiderivative, it becomes this. Okay. Now, if this one has a radius of convergence R, what do you have for this one and this one? Now take a closer look. What's the difference? The difference are, number one, Cn stay the same, so there's no difference. Okay. This part and this part are basically the same. If you do the ratio test, you still got exactly x minus a. X minus a. No matter you start, basically what you do is you shift everything to be 1 power bigger or 1 power less. Okay, but the ratio is still just 1 power if you go from an to n plus 1. So the only difference will be this n here and n plus 1 here. But as we said before, remember this one r equals 1. If you pair it with a geometric, this will actually shrink or stretch your r, simply because your power is a geometric. You add another geometric, they're comparable, so they're going to shrink or stretch. If you give it a factorial, which dominates geometric, then you don't look at this anymore. You just look at where is the factorial. If it's helping, negative infinity to infinity. If it's not helping, doesn't converge at all. Okay. But now if you think about what happens if you add an n square, then we say the n squared compared to geometric is nothing, because this is a polynomial or power. This is an exponential. So if you compare these two, this is nothing. So that it will not change your r. The only thing this one can change is your ending point. Okay, that's what we said last time, and which is exactly the same application here. Going from here to the top to the bottom, you basically have the same geometric with the same ratio, x minus a, absolute value, okay, with the same r. You just added two polynomials. One is n plus 1. It should not change the whole thing, except just for the ending points. Okay, so I won't do the example because there is nothing to do here. But this is some common idea you want to keep in your mind. That is, if you have some power series, okay, you find it by taking the derivative and then take the integral back, or you take the integral first and then take the derivative back. The answer is it's almost safe to always do so. And the only thing you are not too careful about are the ending points of the interval of convergence, because the interval of convergence will roughly stay the same. Okay, the only thing can change will just be the ending points. Okay, So that is what we have. Let's try another example just to make sure. This time we have the idea. Remember, you're shooting for. I'm shooting for a video here. You can pause anytime and reverse and look at it anytime. Okay. There's no interactions between you as audience and me, so there's no time for your questions. Sometimes you may feel like I'm going too slow, too fast. Okay, because I'm just going straight forward. 1, 2, 3, 4, 5. There's no person, two people stopping me, and I couldn't see your reactions. So you always have the option to go back and rewatch. For me, I would just go with the regular pace I have. Okay. Remember, the formula we're looking for is something like that. Number 1, they clearly don't look the same, so algebra probably won't work. Number 2, maybe you can achieve something like this by taking the derivative or the antiderivative. Which case do you have? Try it, and you will find derivative will definitely work. Okay, then what we need to do is find the power series of this, and then take the integral back. Fairly easy. You need a minus here, so just put a minus x here. Take the -1 to the n out. Keep here. So you are going to take the antiderivative of this. This is just a constant. The antiderivative of this is hard because you need to use the chain rule. So how about we just take the -1 out? Then we only have to do the antiderivative of this. Okay. Then we need to take the antiderivative. You can use the formula we wrote down, or you can simply use your integral skills. Okay. Constants stay the same, just the power. The interval of convergence stay almost the same because I just added another polynomial on the bottom. Okay. Remember, when you take the integral, plus c. So what we have here is not ln 1 plus x yet. Not until we figure out what c is. To find what c is, we plug in some number. I would suggest always plug in a number such that the power series becomes 0, which means you plug in the center. Therefore, plus a 0. That's it. Okay. Again, finish by yourself to find the interval of convergence. I will give you the answer, but you will need to do it yourself. Okay. In the exam, I will ask you to do both the power series and the interval of convergence. Okay, good. That's basically what we have for this section. I promise you, given any random fx, I try to help you to find the power series. Clearly, I didn't give you that because I only give you one, I can almost say corny formula, so you can only do things look similar or things which are related by taking the derivative. That's not much. You have all kinds of functions you can have. For example, you can have e to the x, cosine x, sin x, cosine inverse x, ln x, all these kind of functions. For example, like these things are not related to this one at all. Then how do we find the power series for any function? That is the question. Okay. We don't like just this formula because it's too restricted. Only maybe 7 or 8 or maybe 20 functions we can do which look similar to this. How about any function? That's a good question. And let's think about how do we do that. Let's think about, for example, the most popular one, which is e to the x. How do we find the power series of e to the x? Okay, so let me actually write it down. Let's make it centered at a equal to 0. We can find other centers later if we want, but let's just do 0. Because it's centered at 0, I'm going to use x minus xn. If it's centered at 2, we use x minus 2 to the n. Okay, Cn. Now you realize to find the power series of a given function, you basically just need to find what all the Cn's are because the powers will always look the same. It's a polynomial. Okay, for example, like this is going to be a quadratic no matter what ABC you plug in. Your job to know a quadratic is actually figure out what A and B and C are. Okay, you don't do anything with the x squared, x, and 1 because they are standard. So we just need to find all the Cn. Okay. Well, let's take a look. So basically, you're saying C1, C2, C3, ... And you don't know all these coefficients. You do know they are listed as x, x squared, x cubed, right? You want to find all these Cn's. Well, just given what I wrote down, I can plug in some numbers. I want to plug in x equal to 0 and see what happens. On the left, I have e to the 0, which is 1. On the right, what do I have? Then you realize, okay, it's pretty nice because if you plug in x equal to 0, anything with x or x squared or x cubed will all go to 0. Only this one remains, so at least I find the first coefficient. It's 1. All right, that's good. But we still have C1, C2, C3, all the others to find. Well, now I'm going to do a trick. I am going to take this one. I am going to take the derivative. That's still e to the x, right? But that should be also the power series after taking the derivative. So what's the derivative of C0? 0, because it's a constant. What's the derivative of C1x? It's just C1. Derivative of C2x squared, it's C2 times 2x, plus C3 times 3x squared, which come from x to the cube, plus C4, x to the 4x to the cube, which come from x to the 4 before you take the derivative. So we got all these. Good so far? Still true. Then if you plug in x equal to 0 this time, you still have e to the 0, which is 1. On the right-hand side, this is 0. This is 0 because you have an x. You're plugging x equal to 0. It's 0, 0, 0, 0. So you'll find only C1 is left. So C1 equals 1 again. What did you do? You have a power series which has x. You take in x equal to 0. All the x disappear. Only the first term remain. You got the first number. After that, you take the derivative. Now this one goes to 0. This one becomes a constant. Everything after that still becomes 0 when you're taking x equal to 0. So if you take x equal to 0, all of these terms will be gone. C1 will be left. With the same analogy, how do we find C2? We want this x to be gone. Otherwise, if I plug in x equal to 0, this term will become 0. I lose C2, right? To make x gone, what's going to happen? You just take the derivative again, which means take the second derivative of e to the x, which is still e to the x. You plug in x equal to 0, you still have 1. Okay. On the right, however, this is 0. This becomes 0 now. You take derivative for once, it's a constant. You take it for twice, this one becomes 0. This one stay. Okay. This one, derivative of x squared. What do you realize? You realize if you take the derivative for twice, then the first term is gone, the second term is gone, the third term becomes a constant because originally you come from x squared. You take the derivative for twice, you reach a constant. Anything after you, x cubed, x to the 4th, you take the derivative for the twice. This one will still have a leftover of x. Okay. Then if you plug in x equal to 0, they're all gone. The first two are also gone. C2 remain. Then in this way you can solve for C2, which is 1 over 2 to the factorial. Try to do this yourself. Try to see the pattern. And now I think we're ready to generate the idea for any single coefficient. Let's take e to the x from the beginning. I will give you the formula for every single coefficient, once for all. Okay, this is the power series, right? I write everybody up to this term, this term, this term, and all the term after. Okay. Now what I want to do is I want to take the derivative for n times. What's going to happen? Well, think about it. If you take x to the 7 for 7 times in terms of derivative, what's going to happen? Well, if it's x squared, you take the derivative for 3 times, it becomes 0. If it's x to the 6, you take the derivative for 7 times, it becomes 0. So if you take the derivative for n times, everybody up to x to the n minus 1 will become 0. Sounds good? Okay, so take this as an example. If you take something for 7 times derivative, if it's x to the 5, it goes to 0. If it's x to the 6, it goes to 0. Okay, so as long as your power is less than 7, after you take the derivative for 7 times, it goes to 0. So everything up to n minus 1 will become 0 after you take the derivative for n times. Okay. What about x to the 8, x to the 9, x to the 10? Well, if you take the derivative for 7 times, because these powers are bigger than 7, you're definitely going to have an x left, or maybe an x squared left, maybe an x to the cube left. All right. So you are going to have sum x, sum x squared, sum x to the cube coming from all the terms after this one, okay, because you're bigger than n. Good so far? Now, is that a problem? Well, remember, you take the derivative of e to the x for n times, it's still e to the x. Now, if you plug in x equal to 0, then this one becomes e to the 0, which is 1, which equals 0 plus, and then all these x will be gone once you plug in 0. Good so far? But there will be a term which does not go to 0, which does not contain any x anymore. This term will remain. What is that term? Okay, to see a same analogy, x to the 6, x to the 5, let's say you take the derivative for 7 times, right? For 7 times. Okay, what's going to happen? X squared dot all the way up to x to the 6, they're all gone if you take the derivative for 7 times. X to the 8th, x to the 9th, x to the 10th, they will all have x squared term, x cubed term if you take the 7 with some coefficients. But once you take x equal to 0, they will all be gone. You will have 1, which is e to the 0. So the only thing left will be this x to the 7 here. What does it give you? It gives you 7x to the 6, then 7 times 6, x to the 5th, 7, 6, 5, x to the 4th. You keep going. And then you take the derivative again. That will be the only term that does not have x, but does not go to 0 either, because you are exactly the same power as the derivative. You take x squared for twice derivative, you definitely receive a number. You take x to the 4th to 4 times, you definitely receive a number. It's not 0, it's not something with x left either. Okay? Because of that, this goes to 0 after you take the derivative. This goes to 0 after you plug in x equal to 0. The only one left will be the derivative of this one by n times. You see n stay? As far as you can see, we have n times n minus 1 dot dot dot. This is n factorial times 1, because you take exactly the same number of power. This gives you 1 equals Cn times n factorial. Cn equals 1 over n factorial 1. We just solve it for any n. That means C0 equals 1 over 0 factorial, which is 1. C1 equals 1 factorial, which is 1. C2 is 1 over 2 factorial, which is 1/2. C3 is 1 over this, which is 1/6. Then e to the x equals this, which is 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x to the cube, and dot, 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 dot. Okay? That is awesome. We just found the power series of e to the x. Okay? It's a long process, but I think you can trust it. So go back and rework it. I actually put the formal steps here in the notes. You can try to compare with my notes. Okay, this is just a rough idea here, which is not too careful, not well organized. Rework it, see the logic. Okay, because later we are going to use the same logic to find it for every fx, not just for e to the x. Okay. Then we can actually finally get rid of this stupid formula, which is too restrictive. We can do it for every single term, single function, if feasible. Rework it. Okay. The second thing you can think about is this. That is, what is the interval of convergence? Because we know e to the x is a nice function, right? You can prove by yourself. I'm just going to show you really quickly. This is geometric, right? This is factorial. What did we say? Factorial dominates geometric. So if you really do the ratio test, geometric compared to factorial is nothing. And this factorial is helping. So this one is convergent from negative infinity to infinity. That means if you have the function of e to the x, you can actually approximate it with a polynomial perfectly. Everywhere. It's not just it will work here. Like last time we showed, it only works between -1 and 1. This one is going to work for the whole thing. Okay, that's why, again, another evidence for why e to the x is such a nice function. Probably it has something to do with this fact. The derivative is itself. Okay. Number 3. Now, what is e? 2.72, right? Roughly something like that. Before we just told you what e is. But now you can actually verify by yourself because you know e to the x is this. Okay. Then e to the 1, which is e, is going to be sum, which is 1 over n factorial, because 1 to the any n is 1, which is 1 plus 1 plus 1/2 plus 1 over 3 this. Keep going. Now if you just want some approximation of e, you can take the sum of the first, maybe, I don't know, 5 terms. Use a calculator. This is going to be 6 plus 1 over 4 factorial, which is going to be 24, and plus 1 over 120. Take out a calculator, find this number. You will find it's actually very close to the real e. Okay, I actually did with 10 using calculator. I find a number. Okay, this is what I what I did. I try to approximate e using 10 terms. Okay, I use Wolfram. I find it's a fraction because remember it's finite. It's roughly this in terms of decimal. Now if you check the definition of e online, the definition of e is this. So you can see with only 10 terms, we're pretty close. Okay, we're close to 1, 2, 3, 4, 5, 6, 7, at least 7 digits to the real e. That's great. You can approximate the real value of e with only 10 terms, or even maybe 5 terms, with a very high precision. And do you know why that is true? Because this one converge really fast, thanks to the factorial on the bottom. Factorial makes things extremely small. Okay. That means a factorial is extremely large, which makes 1 over factorial extremely small, way smaller than 1 over, for example, 10 to the n, which is geometric, which has a very small ratio, but this is way smaller than that. Okay, so you only need several terms for this one to converge to the real value, because this one just, become very small really quickly. You really don't care about all the small terms you throw away because they're so small. Okay, so that's roughly what we have. Next time, when we introduce the same analogy, using exactly the same procedure, we find the power series of e to the x to find the power series of any single function, which will involve the derivatives of the functions up to any arbitrary degree. That is called Taylor series. That is probably the most important idea, one of the most important ideas in calculus, Taylor series. But we will do it next time. One more example I want to show you, just quickly for fun. Okay. This is not standard, but let's see. Approximate this. Let's see what we have here. So what we want to do is we want to approximate this one, right? That means we don't have to actually find the antiderivative. In this case, it's easy to find. Plug in 0.5 and 0.0 to do it. We don't want to do things in this way because later I may give you something harder, which is hard to do the antiderivative. I just want to illustrate the idea here and also give you some easy function so you can verify by the other method if your calculation is true. Now, let's think about it. We do know this, which is the power series. That means we do know the antiderivative of this. Which is nothing, but the antiderivative of this gives you plus a c. Good so far? Okay. Now this is actually the antiderivative of this 1 over 1 plus x. We have a plus c. Now in order to evaluate this, usually what we do is we find the antiderivative first, and then we plug in 0.5. We plug in 0. Good so far? Then it's nothing but this. If you plug in 0 into this formula, you just got 0. This will be the value of the integral, which is accurate. Note, I was very careful because I did 0.5. You need this one to be within the interval of convergence, otherwise the series won't work. Then basically that's the answer. But now if you just want an approximation, what you can do is you can simply take whatever precision you want. For example, you can take 10 terms. Which gives you, plug in 0, and use a calculator to find this. That will be your approximation of this one here. So again, if you have a calculator, you can have a computer, even though you need infinite many terms, you can always stop at final term and try to use that thing as an approximation and say, hey, if I can tell you the error is really small, then you can probably trust this one if you don't care too much about the precision. Okay, so that's another good thing about power series by writing things into power series, because you can always stop somewhere. That's when a computer comes into play, because the computer could never do anything infinity. But if the computer but it can always deal with anything which is finite, even with 1 zillion terms. Okay, then doing that will give you a nice approximation if the original function is behaving nicely. Okay, I didn't type it in, but I will put the number here in the notes so you can verify by yourself. Okay, that's roughly the idea of the power series. To wrap up, we basically try to start with this. We do variations like this. Okay, change it to something like this. Now, if you have something like this, we go a detour by taking the derivative, do the power series, take the integral, and to get the power series. Moreover, R stay the same. That means your interval of convergence roughly stay the same. Only the ending points can change. Finally, we say, what if something which does not look like this at all? We have a procedure to find this. Make sure you review that, because next time we're going to use exactly the same procedure. And this time we're going to do the power series for any function using the same procedure. This is called the Taylor series. Okay, one of the most important ideas in calculus. After that, any function, you can locally write it to be a power series, which is a polynomial. Then everything about that function becomes easy because number one, polynomial is easy. Number two, you can always stop after finite terms and say it is a good approximation. Okay, that's all for today.